Alright, I'm going to try some of these synthesis problems, sort of try to step through them all. I may do some of these now and some later. I don't know if I can get through all of them, or maybe I'll try to do all of them eventually, but this may take, this might be over a couple of videos. The process that I say here is get a small stack of your own paper, copy the problem, use pencil, use an eraser, big eraser. Mechanisms are optional and generally not required. And sometimes it gets in the way because it's not really a mechanism problem, it's a synthesis problem. So you really just need to show the reactions, and the mechanism is not what we're really asking for. Start with squiggly lines for CC bonds, and then proceed backward from the product to each intermediate, and then consider working on intermediates. Yeah, like what I mean by point E here, consider working on the intermediates and then fill in the reagents, is if you can figure out what the synthetic intermediates are, but you just can't remember the reagent, well, that's pretty close, and you get really good partial credit for those kind of situations too. Alright, so I'm going to take my own advice. I'm going to get another sheet of paper for each of these problems and kind of try it on my own sheet. So here we got basically a methyl cyclohexane, and we're adding this secondary alcohol. So let's get another piece of paper out, and I'm going to draw it out and try to step through this. Alright, so hopefully this is clear. So problem A. Methyl cyclohexane. So we're proposing a synthesis, and we're making that secondary alcohol thing. Okay, so how do we do this synthesis? You see a squiggly line? Yeah, here's a squiggly line. So we're obviously attaching that 2-carbon fragment. And is it squiggly next door to the oxygen, or is it on the next? Is it directly adjacent, or is the oxygen on the neighboring carbon? It looks like it's directly adjacent. So does that suggest addition of a formaldehyde, aldehyde, ketone, or epoxide? Well, secondary alcohol with the squiggly directly adjacent would be an aldehyde. Alright, so we're going to go backwards, and you can make this alcohol in the last step using a 1-2 process, kind of using the techniques we did on the previous assignment. So we could do this from a Grignard. Well, actually, so we need a nucleophile part and an electrophile part. I think that's going to be the electrophile part because it's got the oxygen in it, and we said it's an aldehyde. How many carbons is that aldehyde? How many carbons do you see? It's 2-carbon aldehyde, so not a 2-carbon alcohol, but a 2-carbon aldehyde. So convert this to an aldehyde, and it would be 2-carbon aldehyde, and then H2O, like that. Alright, so then the other part, we get our thumb or hand or whatever to cover the other side, and we're like, well, that's going to be the Grignard side. So that would be this with an MGBR. Great. We're not done yet, we got to keep going backwards. So how do you make a Grignard? You make a Grignard from the bromide. And how do you do that? You do, the reagent is Mg. Good. And how do we do install that Br? So this goes back to chapter 3, I think. It's Br2 heterolite. Good. There's problem A. Let's see problem B now. So problem B looks like we're going from a tertiary alcohol to a neighboring secondary alcohol. Are we adding any carbons? We're not adding any carbons, so there's no CC bond forming, so like no Grignards or anything. But let's think about how we do that. So what's the net thing that's going on? It looks like we're converting a tertiary alcohol to a secondary alcohol. Can't do that magically in one step. But we do, you might look at this and be like, well, that looks like an anti-Markovnikov alcohol, assuming maybe there's an alkene in the middle. So if we convert this to an alkene, we can turn an alkene into an anti-Markovnikov alcohol because the alcohol is on the less substituted site. So let's just pretend we had an alkene. This is using chapter 12 stuff, right? Say we had an alkene. How would we do that? So you have to look back in your alkene notes, chapter 12 notes, and we can convert an alkene to an anti-Markovnikov alcohol with what? It's a two-step process. Is it mercury or boron? Mercury makes Markovnikov, which is essentially that. We don't want mercury, we want boron to give us anti-Markovnikov. So it's BH3 hydroboration, H2O2, NaOH, oxidation. Hydroboration oxidation. But how do we go this way then? How do we make the alkene? Well, if you look, this I guess would be chapter 9. Chapter 9 we talked about reaction of alcohols to make alkenes, and we wouldn't use a nucleophilic acid like HBr, because if we did HBr you would just turn the OH into a Br, right? SN1 reaction. We want to go to an alkene, so we don't use a nucleophilic acid, we use a non-nucleophilic acid like H2SO4. Cool, there we go. That would convert the alcohol into a highly substituted alcohol to a less substituted anti-Markovnikov alcohol. Simple synthesis. Problem C. Let's look at C now. Okay, what's this? So problem C looks like we're going from an alcohol into a di-substituted alcohol. And now that is actually very easy. All we have to do is just exactly what we did just now, except there's a special way to convert an alkene into a dialcohol. And it was using what? It's a different metal, not mercury, and it's not boron, it's osmium. It's osmium tetroxide, which OSO4 does dihydroxylation like this. So it's the same exact approach as the last problem, but it makes the dialcohol. So this is really cool because it's a great way to practice those new reactions you just learned. All those crazy reactions you just learned, right? So all you do is, to make a dialcohol is start from the alkene. Start from the alkene. Now all you do is a different reaction, which is OSO4. It's the OSO4 reaction, osmium tetroxide. And then it's like Na2S, H2O, or it could be H2S, H2O. It's basically the equivalent of, well, H2S is the same as H2O, except you have a sulfur. And this is 1,000 times stinkier because sulfur reagents stink. But anyway, it's the workup. So OSO4 is the first part. It attaches to the alkene, and then this kind of cleaves it all off. You can use either Na2S or H2S. Okay, and then here it's the same as we just had, so it's what? E1 reaction, non-nucleophilic acid, H2SO4. Great, D. So problem D looks like methyl cyclohexene, and then we're forming, you can see we're attaching this little piece. Let's see if we can figure out how to do that. So I'll copy it now. Alright, any guesses? We already saw a squiggly, right? Obviously that carbon is this carbon, and we're attaching these other 3 carbons, so that's the squiggly line. Alright? So if we just go backwards, I mean, this seems like the last step seems like a pretty straightforward addition of like that as a nucleophile. That is a nucleophile, so what, like a Grignard. Assume that's a Grignard, and we're attacking how many carbons in the other piece. It looks like it's 1, 2, 3. A 3-carbon thing, right? A 3-carbon thing that we're attacking. And the question then is what are our 4 options so far? We know formaldehyde would basically put an OH right there with you know, without that, just a 1 carbon. Or aldehyde, which would be a secondary alcohol there, or a ketone would be a tertiary alcohol right there. But if the squiggly is 1 carbon away from the OH, it's none of those things. It is the 4th one, which is, what's your new one? Chapter 9, epoxide. So, and the fact that it's an alkene doesn't really matter. We'll work our way back. For now, we're just going backwards, right? So we just do envision this, and where would the Grignard be? Well, the Grignard would be right there, right on the right there, MGBR. And what's the thing we're attacking? How many carbons is it? What's step 2 also? Step 2 is water. It's a 3-carbon, which functional group? Epoxide. 3-carbon epoxide. So that carbon attacks the terminal carbon of the epoxide, opens it up, makes that. Now we just got to work our way back to the alkene. So how do you make a Grignard? You start from the Br. And what do we add? Magnesium. Okay. Now we're almost there. We just have to dig into our chapter 12 knowledge now. How do we apparently convert an alkene to a Br, a single Br? It's not a double Br, it's a single Br. And it appears to not be a Markovnikov Br, because if it was a Markovnikov, the Br would be right there. It's an anti-Markovnikov Br. So we're adding HBr, right? We're adding HBr. So it is HBr, is the reagent. But in order to get anti-Markovnikov, it's not just HBr, it's HBr plus something. What's the something for anti-Markovnikov hydrobromination? Peroxides. HBr peroxides is the magic trick to do it. Anti-Markovnikov Br. Cool problem. That's D. Okay, problem E. Let's see if we can do problem E. So it looks like we're going from a bromocyclopentane to this guy. We're obviously making some bonds, so there's going to be at least 2 squigglies. And it also says, how many ways do you know how to make ethers? The answer is 1. Actually, I guess there's 2. You know SN2, which is the Williamson method. We also know SN1, which is kind of like for tert-butyl ethers, which is a protecting group. I think we'll see that again later. It's a protecting group, PG, protecting group. So, but anyway, making of a methyl ether like this is a very easy SN2. So we're going to do a Williamson ether synthesis there. Let's try that on my sheet now. So I'll redraw it. This is problem E. Bromocyclopentane. I rotated it around a bit, but that's what we're doing, right? Let's do this retrosynthetically. So it looks like what squigglies do we got? Well, we start with the 5 carbons. We end up with this thing with apparently like 8 carbons. Obviously, that's a squiggly. We added that piece. But we also, it looks like we have added the ether. And ethers are made from an alcohol. So basically that would be the alcohol, OH, and a what? A SN2 electrophile, so it would be like that with a leaving group on it, right? What's a leaving group? Like iodide or bromide or something like that, right? So you can make this from the alcohol. So let's just envision the alcohol. There's the alcohol. And then what are the reagents for a Williamson ether synthesis? First you need to take off the proton. So this is chapter 9. Chapter 9 is the Williamson ether synthesis. Here, step 2 is not water. It's actually a base. NaH is usually the base we use for a Williamson. NaH. And then we need an alkyl halide. So the base takes off the proton and makes a O minus. O minus, right? O minus is a nucleophile. You've got to attack something with a leaving group like methyl with a leaving group on it. So I might say ICH3. Methyl. So it's essentially the mechanism is H minus. H minus takes off proton, makes O minus. O minus attacks this carbon, kicks off the iodide, and you get the methyl ether. So at this point, we still got to attach this thing, but this is actually really easy now because it's kind of like, you know, we're used to this sort of strategy. This is just Grignard stuff, so we can just do this from the Grignard. So MgBr is the nucleophile. How many carbons are we adding? Looks like we're adding 2 carbons. It's a secondary alcohol. Make a secondary alcohol from formaldehyde, aldehyde, ketone, or epoxide. Especially with a squiggly right next door to the oxygen. Is it a 2-carbon aldehyde or a 2-carbon epoxide? 2-carbon aldehyde or 2-carbon epoxide? The way we know it's a 2-carbon aldehyde is because the squiggly is right next to the OH. So 2-carbon aldehyde, there we go. What's step 2? Step 2 is H2O. And how do we convert a bromide into a Grignard? Mg.